A boat is moving to the right with a constant deceleration of 0.3 meters per second squared. When a boy standing on the deck D throws a ball with an initial velocity relative to the deck which is vertical. The ball rises to a maximum height of 8 meters above the release point, and the boy must step forward a distance D to catch it at the same height as the release point. Determine A, the distance D, and part B, determine the relative velocity of the ball with respect to the deck when the ball is caught. So, this is a tricky question because we need to consider the relative motion of the ball with respect to the deck. Now, the deck of the boat is moving strictly horizontally, which means the vertical motion of the ball we can treat as we would normally, essentially ignoring the motion of the boat. We can analyze the vertical motion of the ball. So we're going to start doing that. And our main goal here is to first determine, given the height that this ball travels, what was the initial velocity, the initial y velocity that the ball was thrown with, and how long does it take the ball to follow this trajectory? Okay. So the first thing I want to do is solve for the initial y velocity that the ball was given by the boy in order for it to reach a height of 8 meters. So we're going to start with the following equation, that the y velocity minus the y velocity squared minus the initial y velocity, we'll call that vy0 squared, has to equal minus 2 times the acceleration g times the y max, the maximum distance the ball reaches. So in this case, in this particular problem, our y max is 8 meters. And when the ball reaches the apex of its arc, the y velocity is, by definition, 0. So we're left with 0 minus vy0 squared equals minus 2g times 8 meters. We can now solve this for the initial velocity. So I cancel out the minus sign. I have vy0 squared equals 2 times g. G is 9.81 times 8 meters. I take the square root of both sides and I have vy0 equals the square root of 2 times 9.81 times 8. And this works out to be 12.53 meters per second. So we know that the ball was thrown with initial y velocity at 12.53 meters per second. Now that's not what the question was actually asking, so we're kind of working our way towards what we want to get at, which is the distance d the boy has to walk to catch the ball. In order to get there, we want to first now, our next step is to figure out the amount of time that the ball spends in the air. So in order to do that, we're going to use our kinematic equation that the distance traveled, y, equals v0yt minus 1/2 gt squared. In this case, we're going to consider the full trajectory of the ball. The ball starts at a distance of 0, but it also ends at a distance of 0. So the time it takes from the ball to start at its initial height and end at its initial height, both at the deck of on the platform of the boat, we have 0 equals, well, v0y we just determined was 12.53 times t minus 1/2 gt squared. So we can pull out a common factor of t, and we have 0 equals t, all multiplied by 12.53 minus 1/2 times g times t. So there's two solutions to this. One solution is that t equals 0. That's the trivial solution. At time t equal to 0, we know the ball is at y equal to 0. But the second solution comes from setting what's in square brackets to 0. So 12.53 minus 1/2 gt equals 0. And we have t equals 2 times 12.53 divided by g. G is just 9.81. And when you work this out, you get t equals 2.554 seconds. So that's the time that it takes for the ball to start here, to be released by the boy, and to go back to the same Y position, which is that the ball started at. It takes 2.554 seconds for that to take place. Okay. Now the reason we were able to treat that so simply, again, is because the boat is moving strictly in the horizontal direction. If you remember, the y and the x components of the velocity are decoupled. So we could treat the horizontal and the vertical motion separately, and since the boat is strictly moving in the horizontal direction, we could treat the vertical component as we would normally. Now we need to start to think about what is the boat doing while the ball is undergoing this motion. So, when the ball is thrown, the boy throws the ball with an initial speed that is strictly in the y direction. However, at that instance, the boy himself is moving to the right with the speed vd, the velocity of the deck. What that means is that the ball, even though the boy throws the ball directly upwards, the ball will leave the boy's hand with a horizontal component of the velocity vd. So just to put that into perspective, from the reference frame of the boy throws the ball with a velocity that's straight up and down. So from the perspective of the ball goes straight up. However, from the perspective of a person that's on the shore watching this take place, so here is the deck, from another observer who's on the shore far away, it appears to them that the ball is actually thrown like this, with one component vd, that's the velocity of the deck at that time, and another component, that's the v0y, which you already found. That was 12.53. So what this means is that in the x direction, the x position of the ball, we'll call that x sub b, equals whatever the initial velocity of the deck was, we'll call that v sub d, times how much time has elapsed. The boy moves along with the deck of the boat. The x position of the deck of the boat, we'll call that x sub d, equals that initial velocity of the deck minus 1/2 times a sub d, where a sub d is the deceleration of the deck, times t squared. The distance that the boy has to walk on the deck in order to catch the ball is the distance of the boy with respect to the distance that the ball travels with respect to the deck. That's x sub bd. And so x sub bd is defined as x sub b minus x sub d, which in this case is vdt minus 1/2 a dt squared. So this x sub bd is 1/2 times the deceleration of the deck, a sub d, times t squared. So for this particular problem, it's 1/2 times 0.3 times 2.554 squared. And when I work this out, I got that distance that the boy has to walk. This is the distance that the ball moves with respect to the deck, x sub bd, is equal to 0.9786 meters. The next part of the question asks to find the relative velocity of the ball with respect to the deck when the ball is caught. So what we want to find in this case is v sub b d, the velocity of the ball with respect to the deck. Now, the velocity of the ball has, as we discussed, both an x and y component. The x component is just whatever the velocity of the deck is, so we'll call that v sub d, and that's in the horizontal or x direction, so it's I hat. And then there's an upward component, and then when the ball lands, it's not an upward, it starts off as an upward component, but when the ball comes back to the deck, it has a downward component of its velocity, which is negative 12.53 meters per second, j hat. So this is the velocity of the ball when it comes back to the deck. Now the velocity of the deck when is as a function of time is that initial velocity of the deck, vd0, let's call this vd0, that's the initial velocity of the deck, minus the acceleration of deck times however much time has gone by, and this is all times I hat because the velocity of the deck is in the I direction. So these are vectors. These are all vector quantities. So now we can find v sub bd. V sub b slash d is vd0, the initial velocity of the deck, times I, minus vd0 minus adt, again times I, minus 12.53 times j. So this, therefore, these cancel out. The vd0 cancels out, so there's no dependence on vd0. And we get that this equals AD, the deceleration of the deck, times time, I hat, minus 12.53 j hat. So the velocity of the ball with respect to the deck at the time when the ball makes it back to the deck, we can now put in these numbers. AD is 0.3, time is 2.554, so we get that this is 0.766 I minus 12.53 j. So the way this velocity vector appears to an observer that's outside of the boat, let's say on the shore, if here is the ball, it has a downward component of 12.53. It has a horizontal component of 0.766. And the velocity vector, therefore, looks like this. Straight there. Wow. And the velocity vector looks like this. And the velocity vector looks like this. The magnitude of the velocity vector, the magnitude of v b slash d, will equal the square root of 12.53 squared plus 0.766 squared. So the magnitude comes out to be 12.55 meters per second. And the angle that the ball makes with the horizontal, as defined here, well, the tangent of that angle, which I called phi, is equal to the opposite, which is 12.53, over the adjacent, 0.766. And when you take the tan inverse of both sides, I got that phi, the angle, equals 86.5 degrees.